Hi, today I wanted to make a video talking about I think an interesting relationship between the delta head of a pipe segment and the associated flow rate in that pipe segment. The first thing I'm going to do here is write out an energy balance. In this pipe segment, we could have an associated injection work, right? So change in pressure over the density. And then we also could have a change in potential energy. And we could also have a change in kinetic energy. And then any energies associated with these terms could be the result of maybe non-flow work per unit mass. So maybe like a mixer or compression of a fluid, something like that. And then also, importantly for our problem in particular, is frictional heating. So this is kind of the character that I usually see for frictional heating. That's kind of arbitrary, but just to make that clear, that's the symbol I'm going to be using for frictional heating moving forward. So the first thing I want to do here is I want to assume I have a pipe that does not have a change in kinetic energy. So maybe not maybe there's not going to be a change in diameter along the pipe or something like that. And then also, let's have no non-flow work. So, maybe no blending. Essentially, we're going to, if we can imagine, we're just going to have a pipe segment that can have changes in pressure and changes in height. So, with these terms here, a useful thing we can do is actually, we can express this equation using head. So we can do that by dividing everything by g. So let's go ahead and do that. Divide by g here, divide by g here, and we'll have delta P over the density times gravity plus change in height equals negative frictional heating. Okay. So the reason that maybe expressing this frictional heating in terms of a delta head is really that this is kind of practical because this has an associated change in height, right? So this term actually, our pressure, we can write this as rho gh, right? Fluid statics. And these cancel out, right? And you get an associated height. So really, that's going to be very useful for us because we're going to have frictional heating with associated differential head. So why is this useful, and what can we do with this? Well, going off here, there's many different ways that you can handle this frictional heating term. So how I'm going to approach this problem is I'm going to use something that's pretty common, I think, and that's utilizing a fanning friction factor. So I'm not going to go through the whole derivation for this. It's basically, you basically can get it from an energy balance just like this, but essentially we can rewrite this frictional heating term as 4 times something called the fanning friction factor, and that is multiplied by the ratio between the length of your pipe and the diameter of the pipe times v squared over 2. And furthermore, there's something interesting that is associated with frictional heating as well, and you can also express it like this: k times v squared over 2, where this k value is found, it's pretty much pretty much derived from the relationship between, maybe if you have like a sudden expansion or, a joint or a bend or something like that. And, you get to this by the ratio of the diameters of the piping associated with that change. So we can combine these two, and factoring out of V squared, right? You can have a K plus 4F times L over D V squared over 2. Now this is going to be particularly useful moving forward, and I'm going to write this all together. So now this term here is our delta head, and from here on I'm going to use lowercase h to represent head, not enthalpy. So 100%. This, in my case, I'm going to use lower h for the head. So now I'm going to say this delta head equals, my new frictional heating term. So we'll have K plus 4 times my fanning friction factor times the ratio of the length of the pipe over the diameter of the pipe times the average velocity in my pipe squared over 2. So now looking at this equation here, we kind of have a grasp of what a differential head means, a length, a diameter, a velocity. But there's kind of this abstract term here, right? This is a fanning friction factor. So what is that? Basically, maybe a good way to visualize it, I would recommend maybe Googling something called a Moody diagram. So if you look up Moody diagram, you're going to see, actually I'll just kind of give a rough little sketch to give an idea. If you Google it, you can find plenty of charts. So basically, you might have a region for turbulent flow, looking like that, and then maybe you'll have a section with laminar flow, and then you'll have a transition range there. So basically, on this axis you're going to have some associated roughness factor, and that has to do with the material of your pipe. So you can see this roughness is it's going to be associated with a friction factor, which will be over here. And you can see that's going to be pretty useful because, even though this is not a linear relationship, as the Reynolds number, on the x-axis we're going to have the Reynolds number. So as you kind of increase your Reynolds value, your Reynolds number, you're going to have a pretty good approximation for your friction factor. It's going to stay relatively stable. So definitely, it's definitely a useful way to approach frictional heating. Now, how am I supposed to find this, right? Now, I think some of the most common ways to approach this is using experimentally, derived equations. And the one I'm going to be using moving forward is something called the Churchill equation. And I'm not going to bother writing it out. It's, it doesn't really mean much theoretically. So all we really need to know is that with this Churchill equation, there's some relationships, and all we really need to know in order to find our fanning friction factor is a Reynolds number and something called epsilon over d, where d is the diameter of your pipe and epsilon is some roughness factor, kind of like an average roughness. So from there, going back to this equation, we'll know our fanning friction factor. And, for a given pipe, assuming that the K value, assuming the K value associated with any expansions or joints, things like that, the length of your pipe, the diameter of your pipe, also the terms associated with your Reynolds number, so your density, velocity, diameter, and viscosity. If you know those things, you'll notice that the delta head in the velocity and in turn the flow rate, right, using your cross-sectional area of the pipe, you can solve for one or the other if you know one or the other, right? So now let's consider a scenario where, for example, we know the flow rate, and in turn we know the velocity. So what we're solving for in that case is the delta head. So I'm going to rewrite this. Delta H equals RK plus 4 times the fanning friction factor, say that 3 times fast, and then the length over the diameter of the pipe times velocity squared over 2g. I actually forgot that over here, just to clarify, right? We said we can express frictional heating with this term when we divide it by g, right, up here. I really should have carried a g over here. So just to correct that, right? So now in this case we're saying, okay, we know Q. So Q is known. And in turn we know the velocity because Q equals our average velocity times the cross-sectional area of the pipe. Right? So V equals Q over A. And for a pipe, we could say V equals Q over, area of a circle is pi r squared, but let's keep things in terms of the diameter, right? So instead let's say pi, oh that's a bad pi, times d squared over 4. Right, perfect. So now we know this V, and really it's a straight shot then, right? All we have to do is rewrite this V in terms of the flow rate and the diameter, and then we can calculate delta H, assuming we know the length, the diameter of the pipe, K, and then also the Reynolds number and the roughness factor. Okay? So that's one approach, and if we consider the other one, maybe we know the delta head and we're trying to find the velocity. I'm going to rewrite this as this. Now, the reason I'm doing this is because there's a problem here. And that's because if you notice, you could say, oh, well, the velocity is here, maybe we can just solve for that. Can't really jump to that conclusion because our fanning friction factor depends on the Reynolds number, which also depends on the velocity. And that can get pretty gnarly. That's this is going to be a pretty nasty nonlinear equation. So, and we're going to kind of approach that problem in a second here. We're going to move over to Python. But what we're going to do here is, if we're saying we know our delta head, this is known. And, this term here represents the frictional heating, but it also represents the delta head, right? So we want to obtain a delta head equal to the actual delta head by making a guess for the flow rate, right? So when we do this, we're going to use a Newton-Raphson estimation to iteratively, adjust our guess for the flow rate until this equation is satisfied. Okay? So let's move over to Python now. Actually, I've made another mistake again. Sorry about that. Again, going back to this frictional heating is negative. So, when I'm plugging in this expression for it, really, this needs to be negative, right? And again, it'll be negative here, and if I'm moving over this side of the equation, it should be a positive. So, sorry about that. So let's go over to Python now, and let's create some functions for both of these situations, right? Okay, so moving over to Python here, the first thing I'm going to want to do is import some modules. So first off, I'm going to want NumPy, and something else I'm going to need is a tool to solve for the roots of an equation. Remember, if we knew a given flow rate, we could determine the differential head, and it would be a straight shot calculation, right? But conversely, it would be a bit harder if we knew the differential head and we were trying to find that flow rate. And that's where we get into that difficult nonlinear equation and where we utilize a root solver. So from SciPy, we are going to want a Newton function, right? If we look at this, find a zero of a real or complex function using Newton-Raphson method. So that will be helpful for us. I think the first thing we're going to want to tackle is how we handle our fanning friction factor. And like I said earlier, we're going to use something called a Churchill equation to determine that. And obviously in both situations, we're going to have to utilize the Churchill equation. So in a separate tab, I went ahead and tested this out. I'm just going to copy and paste that in, but I'll explain what I did. Because I didn't want to spend the time typing this out, because it essentially, I didn't explain this through theory. This is just something that's been determined experimentally. So we have a function here, and the required parameters for it are the Reynolds number and this ED, which is what our epsilon over D is, right? That material property, the roughness of the pipe, and the Reynolds number. So basically, with those two parameters being satisfied, we can use the Churchill equation to determine the fanning friction factor. So that's good. Now we can move on to creating two functions for our two different scenarios. First, let's tackle the easier scenario, which is where we know a flow rate, we know Q, and we want to find the differential head. So let's create a function to find that differential head. Oops, let's call it del head. And we're trying to find the del head for a given flow Q. Okay? So if I'm looking at this equation, if we're trying to find the delta head, we're going to need to know a K value, a fanning friction factor, a length of the pipe segment, the diameter of the pipe segment, the average velocity in that pipe segment, the gravity in that pipe segment. So I think first off, I'm just going to, because we know that this is just going to be a straight shot calculation. So first of all, it probably would be a good idea just to, type out what this calculation would be, and then we'll work backwards and figure all the information we need to be able to actually solve it. So looking at my equation, we're going to have a negative our K plus 4 times our fanning friction factor. Let's use a lowercase f, and then that multiplied by the ratio of the length of our pipe times the diameter of our pipe, and then that will be multiplied by let's use a capital V, by our average velocity squared over 2 times g, our gravity. So looking at this, kind of let's go ahead and you know, if we're saying that we need you know, all these values for this to work, let's give some values here. So we know gravity, you know, that's like 9.81 meters per second squared. We'll just give a k value of 1. Let's say our length is 100 meters. Our diameter is, say, like 0.1 meters. And also we'll need an E, or epsilon over D, or ED. And let's just say that's 0.01. And for our Reynolds number, we're also going to need a density. So let's say rho 1e to the negative 3. Okay. Also need a mu for the viscosity. Let me Google that real quick. What is the viscosity of water? Blah, blah, blah. 1 centipoise at 20 degrees Celsius. So that'll be 1e to the negative 3. Okay. So then going back to the parameters of our function, you know, we have all these values. Oops. So we're going to have to supply those when we want to use this function, right? So we're going to need a k value, a length, a diameter, and associated roughness. Gravity is not going to change. You know, let's keep things simple. This is just a pipe, and we're going to have water in it, right? So we'll have we'll say we have a constant density, constant viscosity. Gravity's not going to change, right? So that should be all we need for this to work. Okay, times our diameter divided by our viscosity, mu. Okay, so we know that. We know our epsilon over d. Okay, yeah, we know length, diameter, velocity. We know our velocity, but we're given a flow rate, right? So we're going to need to convert our flow rate to a velocity, so our function can use that. So then our velocity, flow rate equals our average velocity times our cross-sectional area. We can take our given flow rate and divide it by that area. So for our pipe, that would be pi times our diameter squared over 4. Actually, let's go ahead and name pi as a variable, so I don't have to keep retyping mp.pi. Run that. Okay. Okay. I think that might be good. Let's go ahead and give it a shot. So let's say del head, and let's give a flow rate of like 0.1, and then we already supplied a k value, length, diameter, and a roughness. So let's see what happens. Got an error. Local variable v reference before assignment. Reference before assignment. Oh, I got to change the order of this because the Reynolds number doesn't know what v is yet. Alright, let's see if that fixed it. Nope. An indent does not match any other. Does not match outer indentation level. Okay, so it seemed to work. Let's see what. Let's. Okay. So we didn't get an error there. Let's see if we get something that seems reasonable. Okay, so we got negative 2.59. So that's saying if our flow rate is 0.1 meters cubed per second, we get a differential head of something like negative 2.59. Yeah, I think that makes sense. Good. And I think that makes sense because, you know, if you think about it, right, if we have a drop in delta head, so we're moving from an initial position and then our pipe is moving to a lower position. So you would expect the flow to be going in that direction, right? If we're going to think about this as, you know, from our initial position to final position, if our flow is moving according to that, we could say that that's a positive flow if it's going in that direction. So another thing to consider is if someone, if we have a negative flow rate, right? Let's say our flow, yeah, okay. Well, let's see what happens. That looks a little weird. I don't like that. I'm just gonna rerun everything, and we'll use negative 0. Let's just use that again, I guess. Okay, we got that. It's a weird number. Why are we getting this? Yeah, something's going wrong. These numbers are, that doesn't seem right at all. So if I get a negative flow rate here, Q is negative, which means our velocity is negative, which means our Reynolds number is negative. That's not right. We don't really want this to be negative ever. So let's go ahead and, for the sake of the Reynolds number, let's just take the absolute value of our velocity. So our Reynolds number is positive. When the velocity is being used here, it's being squared. So we'll be getting a positive, or the sign won't be. So then our sign isn't being carried. So then the other thing we want to do is to retain the signage of our initial flow rate. I think it's sine. Okay, so sine, let's retain the sign of Q. Okay, let's see how that does. Aha. Alright, so then this is saying for a negative flow rate, right? If if the end point of our pipe is higher than the initial point, you would probably intuitively expect that the flow would be going backwards back to that initial lower point. And let's go ahead and see what happens if we have a positive 0.5. Perfect, the same value, opposite sign. So in this case, you would expect your flow to be going in the direction of the initial to the final point, right? If we have a drop in delta head, that means the end point of our pipe is going to be lower than the initial point of your pipe. So you would intuitively expect your flow rate to be going in that direction. So that seems to be working all right. So our function, we know it'll work if we give it a positive or negative value. So that's good. All right. So now I'm going to move on to, oh, actually there's one other thing that we should consider here, right? We can take negative values, positive values. We're not going to have imaginary numbers or anything like that, but what if our flow is 0? Because if our flow is 0, we're going, our velocity is going to be 0, and our Reynolds number is going to be 0. So, we should get an error if I put a 0 in here. Let's just test that out. Yeah, invalid value. Okay. So, if we have no flow, in this case we shouldn't really expect any change in head. So let's add a condition. If q is less than like a really small number, let's just say like 10, I guess. And it has to be the absolute value, right? Because if we give it a negative value, that would be an incorrect conclusion that we don't want, right? So the absolute value has to be that big. Oops. So then, if that's the case, then we want to return 0. So now we should just get a 0.0 popping out here. Perfect. Okay, so I think that's probably good. That's as robust as we probably need this to be. We want to be able to handle negative flows, positive flows, and potentially if the flow is 0. So it'd be pretty useful, right? If we have some pipe segment and we know about the geometry of it, and we know a little bit about the fluid itself, right? It's maybe its viscosity, its density, things like that. And the geometry of the pipe, of course, we know like a K, we know the length, we know the diameter, the roughness of the pipe. If we say we want this flow rate, we can we can figure a delta head that'll provide that flow rate. So that'd be pretty useful. But let's go back and consider the other scenario now, right? What if we know the delta head and we want to know the flow that would be associated with that? So in this scenario, if we get an idea of what we're trying to accomplish with this function, we know a delta head, right? So we know a delta head, and we know from the equation I worked out on paper, we know our delta head plus our frictional heating should be equal to 0, right? Assuming the scenario that we've kind of come up with here. So basically, if we know our delta head, we want our frictional heating to offset that delta head so our equation is satisfied and is equal to 0. So we're going to do that by we're going to have to supply a guess, an initial guess for our velocity, and this is where our Newton, this tool is we're going to use it to basically it's going to go through and adjust our initial guess for the flow, and in turn, the guess for our velocity. It's going to adjust that until that frictional heating term cancels out our known delta head. Okay? So let's get started, and similarly, let's call this function flow, right? Because in this case, we were solving for the delta head when given a known flow, and this time we want to calculate our flow for a given delta head. So I'm going to call this d head instead of del head, right? So that makes sense, and we should be using the same exact parameters as our other function, right? It's still the same equation, but we're going to be solving for roots that satisfy our equation in this case. So we should be having the same parameters that our function needs. Okay, I think that's all right. And what is this flow that we're supplying to it? Well, if we think about this, we're going to be supplying, some sort of flow, and that's really going to be our guess, right? So it would be like our Q guess. So what's going to happen is we have our known delta head. So we have our known delta head, and we want to. Okay, so here's what we're actually going to have to do. We want to use I'm gonna call that Q because we're going to use our function from up here, right? If we recall for this function, we were solving for the delta head for a known q. And in this case, we have something very similar, right? We're guessing that we know the q, and we don't know the delta head for this term, our frictional heating term. And we're going to increment that until it cancels out with our truly known delta head that was given. So we're going to be using our function from up top, right? And then we're going to take off our known delta head, which we call d head in this case. Okay? We want to go back and adjust this guess, right? We're going to adjust that guess. So it's going to start out with this guess and slowly, progressively change our flow until this is satisfied. When this goes to 0. So this is ultimately what we want to return, because this will give us the q guess, which really after this Newton function iteratively goes through. When this equals 0, it's going to give us our actual q. The q guess that makes this work, right? So let's see what happens if we try and run this, and let's use I'm actually going to make another cell just for comparison's sake. Oh, I guess I can't make one unless I type something. So let's use this function and work backwards to see if we get the same answer. So let's say for like 0.5 flow, and then K, L, D, and then ED. So let's run that. Okay, we get that differential head. So let's do it from the other way around now. So we're going to say flow, and for our given differential head. So in our case, let's try negative 12.978. That's probably good enough. And then the same K, same length, same diameter, same roughness. Let's see what happens. Okay, we got an error. Bad operand type for absolute. If So is this within Newton? I didn't write that. In Newton. Okay, so we have a problem. We have a problem in Newton. Something's going wrong here. So we made some kind of mistake. Let's think about this. So there's a problem in Newton. So what are we giving Newton? We're giving it this function and this guess. So we guess, and this is our function we're supplying it. So it's possible that maybe there's a discrepancy in the sign. So I'm going to try this with a positive 12.978. Okay, that still gave me an error. Is that the same error? Yeah. Huh. I'm going to change this name. I think it's a little confusing. These different delta heads. It's like, what is the difference between this and this, This is, we already know this for a fact. This delta head is really a guess because we're using a guessed flow. Okay, so let's keep thinking about this. Oh, this is pretty obvious. Okay, so I didn't return anything there, right? So the Newton didn't know what was, Okay, so let's see if that did anything for us. Okay. All right, look at that. This is pretty close to 0.5, right? Because we didn't carry all these decimals. Perfect. So let's. So it looks like it works when we give it a negative delta head where you would expect a positive flow to come out. And let's try for a positive delta head. We expect a negative flow rate, and we get a negative flow rate. The other thing, of course, we want to test is if we give it a zero differential head where you wouldn't expect any flow. And maybe it works out. That's that's pretty dang close to zero. But I think we might as well do something similar and throw in an if statement here. So now, and of course, we want to use the absolute value again, but this time we're using d head known, right? So if the absolute value of this is less than a really small number, what did we use last time? 10. Return 0. So we should just get 0.0 here now. All right, cool. Okay, so our function works, but this guess is this is just any number, right? There's really no rhyme or reason I picked this 0.5. So I'm going to try and make a better Q guess. So we know our roughness of our pipe isn't changing really, and neither is our Reynolds number. The only thing that's changing our Reynolds number is the velocity. So our fanning friction factor is going to be roughly the same. Because if you remember when I was drawing on that piece of paper, for a certain size Reynolds number and an associated roughness, the fanning friction factor is pretty approximate. It's pretty close. It's a very reasonable guess. So that's almost like a guess for the fanning friction factor, and it's a pretty reasonable guess given our situation. So if we know that fanning friction factor, then assuming that, then we can actually go back to our energy balance and solve for our velocity as a guess. And if we know that velocity, right, we can multiply that by a cross-sectional area and get a Q guess. So I'm going to work this out just by looking at it. So I'm going to take some time to double check that this is right. So of course the first thing we're going to be multiplying this velocity by an area. So first thing we're going to want is pi times our diameter squared over 4. And now this is going to be multiplied by what our velocity is going to be. So we're going to have a negative, and what is our delta head in this case? It would be our known delta head, right? And this would be multiplied then by a 2 times gravity, so 2 times gravity, and then that would be divided by K plus 4 times our fanning friction factor, which we're going to go back and really throw in our guess for our fanning friction factor. So I'm not going to leave that. Yeah. Okay, that looks all right. And then we have v squared, and we have to find the square root of this. Okay, so I'm going to pause and take a second just to make sure this is right, because I just kind of did that in my head. And probably would have been better if I did it by hand, but it should be all right. Okay, so then looking at this, we have a pretty glaring issue, but ultimately that should be a very easy fix. So, if we look inside our square root here, our numerator is going to be negative. It has the chance to be negative. So I'm just going to remove that possibility, because really Yeah, it does. That shouldn't matter. So let's take the absolute value of this delta head. Okay, invalid syntax. Oh, that's right. And this. Cool. So this should be correct now. Let's see if we get same answers again with a better guess. So then let's go back and say, assuming that our known delta head is around that, right? Maybe 12.97. We'll round that up. I got an error. Name f is not defined. Right. The program doesn't know what f is. And that's because I didn't give it that good guess. So I'm going to look at a Moody diagram now. So looking at a Moody diagram, I'm going to use 0.02, and ultimately that again, it really isn't entirely important that that's a perfect guess, but at least for the roughness in our problem, it's a pretty decent guess. So this should work now, I believe. Let's check that out. Okay, that's pretty good. And let's see what happens with a positive, right? And then if we do 0, we should get our 0.0. Perfect. So now we have our two functions. So now for any pipe segment where we know about some of the geometry of the pipe, well, really we should know all about. So we know the geometry of our pipe segment, and we know either the delta head or the flow, and we also know about our fluid inside of the pipe segment, right? Its viscosity, its density. So if we know everything, if we know all of that, and we either know the delta head or the flow, we can solve for one or the other, and that'll be pretty useful. So to go a little further, I'm going to make another video. In part 2, I'm going to look at a network of pipes, and I'm going to solve for the flows and delta heads in all the pipe segments.